Good morning, my friends. You're more than welcome to join to my channel, Fundamentals of Engineering with Farhad, Mechanics of Materials. We are about to go through a very interesting example in finding the maximum moment in a beam, two simple support beam with a triangular loading. So in this example, we have two simple support beam AB with the distributed loading which starts from 0 at one end and goes all the way to the maximum intensity of W in the other end. This is a triangular loading on a two simple support beam. We want to calculate the maximum moment in this configuration. To do so, we need to first replace, we can call it like the first degree, and we do know this is a linear loading. We can also call it the first degree. For such case, we need to replace the distributed loading. So if you have it like a rectangular loading with the same intensity of W over the span of beam, then the resultant force was equal to Fr. If we want to replace the distributed load with the resultant one concentrated load like a resultant force, that's the intensity of load times the length, WL. For our case, this time the resultant force so is half of that area. That's a half of WL. And the location of that is 1/3 of length from the support A. So if this is our case, we can easily replace our distributed loading by its resultant, and that's a half of WL, and the location of that is again 1/3 from 1/3 of length from A. We can easily calculate the reactions of supports, which is RA and RB, like 1/3 of WL and 1/6 of WL for the others. So it also makes sense because the resultant force is a more closer to support A, so RA it carries a bigger chunk of energy of load in comparison to reaction at B. Now let's see how we can calculate the reactions at A and B. So if we just replace our distributed load with its resultant, which is a half of W times L, and then summation of moment, for example, about A goes 0, like a counterclockwise is our positive direction. And again, this length is a 1/3 of length from A. And it just simply says RB times the length. This is our RB times the length. This is our RB and RA times the length and counterclockwise moment, which is a positive, times RB times L minus a resultant force times 1/3 of L, and that's a clockwise. That's why we have it like negative. Half of WL times 1/3 of L equal to 0. It simply says RB is equal to a 1/6 of WL, and the summation of moment in Y direction goes 0. It just says these two supports should cancel out the resultant of half of WL. So the summation of RA and RB are equal to half of WL. So if you have one of them, we can easily calculate the other one. So in that sense, it just says RA is equal 1/3 of WL and RB is equal to 1/6 of WL. As soon as we have the load, we can just jump. As soon as we have the reactions, we can jump to drawing the shear and moment diagram. So in drawing the shear and moment diagram, you can easily see for shear diagram, it just simply starts with the value of WL over 6, which is here. There is no loading here as you see. So the reaction brings back the support reaction that brings back the shear diagram to 0 by the amount of RB. Mhm. And if you remember from the statics, dV over dx is equal to W. If you remember this mathematical formula, and now we want to have an interpretation of the geometry of our problem. It simply says the slope of shear diagram is equal to the value of R load. So if this is the load, and this is the shear diagram, it simply says you can easily see there is no loading here, and the amount of loading from B to A is in an increasing format. So if this is 0 here, there is no loading and at the B, and it just increased the amount of loading. It just says the slope of shear should be equal to 0 here, because the slope of shear is the amount of load. And if the pattern of load is increasing, as you can see here, the load is increasing, it just says the formula says the amount of the slope of our shear is in an increasing format. Shear increases on until it reaches its maximum value, which is RA. Mhm. That's an interesting interpretation of this formula. We do have the same pattern as well for drawing the moment diagram. So this is the first degree, the shear is second degree, and definitely the moment is first, second, and third degree. And also, if you draw a line from here to here as well, for example, if we have let's say, if we have a rectangle, triangular shape with the length of L and height of H, if we call this this height like H, it started from a negative WL over 6 and reaches to a positive WL over 6, and the total H is equal to the resultant force, that's Fr is equal to half of WL. So HL is WL over 2. So our H is WL over 2. And we want to calculate it somewhere with the length of X and with the height of Y. Mhm. So in our triangular proportion, one can easily say x over L is equal to y over h. X over total length, which is L, is equal to y divided by h. So if we call this part like x and this is y, we can have this reasoning. The same story for our case for this greenish area. You can see the only difference is now our case is this is L, this is H. Now our case is this one with the length of X and height of Y. One can easily say we can have it like for X over L is equal to Y over H. The only difference you have to consider it like a X over L to the power of 2 because we have like a second degree or an exponential curve. That's only difference we have in comparison to a triangular shape. So if that's the case, with the same logic, we have like x over L squared is equal to y over h for our greenish area here. And it simply gives us like y is equal to WL over 6 because that's a height of this rectangle. And h we already calculated it is equal to the overall FR, which is a half of WL. So it simply says if x over L squared is 1/3, x is equal to L over square root of 3. So we is simply calculated the length of x where the maximum moment applies there. The same story for dm over dv. If you remember, we talked about it earlier. So if dm over dx is equal to shear, a slope of derivation of moment over x is equal to shear, it simply says you can easily see the absolute value. Be careful, the absolute value of shear is decreasing. Mhm. So it simply says the slope of moment is decreasing until it reaches to v equal to 0. That's a horizontal line. And then the absolute value is increasing. So the slope turns and increased in moment diagram. And also if dm over dx is equal to v, you can go with vice versa. The integration of v dx is equal to moment. That says the area under shear is equal to amount of value of moment. So the area under this part is simply the amount of M maximum which we are looking for. So if that's the case, now let's have it like M maximum calculation over here. And that simply says if we have this relation and we know x is equal to L over square root of 3, then the area under this yellowish area is equal to the amount of maximum M. And maximum M is the dashed area or this yellowish area, and that's simply 2/3 of WL over 6 times the length of X, which is, let's get rid, we don't consider this part, X is just this value, times L over square root of 3, and it simply says maximum moment is equal to WL squared over 9 times square root of 3. That's our maximum moment. Thank you. We'll solve more problems in shear and moment diagrams.